All right, now we're ready to see how all this electromagnetic radiation stuff fits in with the model of the atom that we left off at. Here's a little hydrogen atom, and this is in the Rutherford view. There's a little proton in the nucleus, and there's an electron that is orbiting it like a planet around a sun. The attraction between the negatively charged electron and the positively charged nucleus holds the electron in orbit. The electron moves with a certain amount of energy. Kinetic energy is going to determine how fast it's going. You may remember from grade school. Kinetic energy. Keep something in motion. And it's going to be, let me see, I'm losing my markers here. 1/2 the mass times the speed of the electron squared. All right, well, I guess what's important there is that the speed determines how much energy this has, and how much energy it has determines how far away from the nucleus it's going to be. As long as it can cruise along at a set speed, it can do this orbit. But if that speed were to decrease, it would fall into a lower orbit because it would have a lower energy. It would not be able to resist the pull of the nucleus so well, and it would fall into the nucleus. So, can't have anything that is going to reduce its energy because that would cause it to fall into the nucleus. But unfortunately, that's exactly what we think should happen, according to what we've said. Because what do we have here? As this thing whizzes around the nucleus, it's like a vibrating charge. It's like a charge that's oscillating. So this should be producing an electromagnetic wave. A Rutherford atom should produce an electromagnetic wave, and people call this EM radiation. Electromagnetic wave. And that means that, since we said that an electromagnetic wave transmits energy, that as the electron moves around this orbit, it should be beaming out this wave, it should be beaming out its energy to the surroundings. And as it does, it's going to be losing energy. And as it loses energy, it's going to slow down because its kinetic energy is going to get less. And as it slows down, the nucleus is going to be pulling on it. So what's going to happen is that it's going to spiral in and crash into the nucleus, and the atom should collapse. Now we said that an atom is anywhere from 10,000 to 100,000 times the size of the nucleus. So that can't happen. That is not what's happening here, because the atom is bigger than just the nucleus. And if this happened, it would just have the nucleus. So what if the plum pudding thing was right, and except with a nucleus? What if we had a fixed positive charge here, and we had our electron floating out here, and they were somehow stationary? Because we could stop this electromagnetic wave if we could stop the electron from beaming out. So you have a fixed electron and a fixed positive charge on the nucleus, and just have them fixed in space there. Well, that's not going to stay put like that, because there's nothing really that is holding the two of them apart. The attraction of the electron for the nucleus is going to cause it to slam into the nucleus, and you'll get the same effect. So if the electron is moving, it'll lose energy and spiral into the nucleus, and the atom will collapse. If the electron is not moving, it will be pulled in by the nucleus, and the atom will collapse. This is the collapsing atom paradox. And this, when you get a paradox, that shows that something isn't true. Something is seriously wrong here. The Rutherford model must be wrong. This is a common thing to do in science. If you can reduce, or in philosophy, or in logic in general, if you can reduce something that someone else is saying to a paradox where it's false either way, you've disproved one of their assumptions. Now, what are our assumptions here? Our assumptions are, well, we're pretty sure there's a nucleus. We have experimental support for that. But we don't really have support for this orbit that the electron is going around in. It turns out whatever kind of motion it has around the nucleus is going to produce this EM radiation. But it turns out that our assumption assuming that the electron is a negatively charged particle is a particle when trapped in the atom must be false. So there's something wrong with that assumption. And the collapsing atom paradox kind of points us to that. And here's what it's going to turn out to be. It's going to turn out that the electron actually, when it's trapped in a small space, acts like a standing wave. It acts like a wave that its amplitude is related to probability of locating an electron at a point. But you can think of it as a wave whose amplitude is related to the negative charge. You can think of it, the electron, instead of a little particle orbiting, you can think of it as a negatively charged fog around the nucleus. And that's the point that we're going to expand on in the rest of the chapter.